So that was the goodness of fit test. So it's a very important test because many times we need to know whether our data fits the expected distribution. So we saw two different things. This multinomial experiment, which is an expansion of the binomial. We know that there are many steps that we need to follow. We knew how to build the how to build the Excel for this. So we departed from the known probabilities. Then we got a sample. That sample is the observed. So we apply the sample and multiply by the known probabilities for each cell, and we got the expected. So remember, in this case, if I had, so I am expecting, this is kind of the expected value that I believe is gonna, the expected probability. So if I go out and I ask a person, what is the probability that this person is using an accountant as the means for tax preparation? So there is a 15% probability. So, so that 15% probability, given the sample of 340, I should have 51 people that matches this probability. But when I do my survey, I find out that there are 71. So according to this, I am gonna subtract the expected from the observed, square it, then divided by the expected, every single line, and then I am gonna add all these chi-square, all these deviations squared. So I'm gonna find the chi-square test. So remember, this is the chi-square test statistic that I am using. That is based on my data. So in this case, I have a survey. I am observing this data. I have some known probabilities. So based on this, I multiplied the sample size times the probability to find the expected. So now I have my chi-square test. So I'm gonna find the critical value. So remember, for the chi-square, I need alpha and I need the degrees of freedom. So in this case, I'm gonna find the chi-square. Remember, this is a right tail test. So so I have this chi-square test, this chi-square critical. So this chi-square critical is 13.27, and my my chi-square is 43. So here I think I was doing something else, but here this is 43. So my chi-square number here is gonna be 43. So my 43 is gonna be somewhere else, so somewhere in here. Oh no, that was good because I added some other column rows just to
this 35, Professor?
Yes.
Yeah.
Say that again?
It's 35.121, I think.
35.
35.121.
1 to 1. Okay, thank you. So that was the number that we found. Remember, I added these two cells. So the original example, thank you, Nicolene. So the example, that was our values. So because it was inside of the rejection region, we reject the H naught, so we can make the proper call. We need to know which one is the claim. So in this case, this is the claim. We are rejecting the claim, so we have enough evidence to reject the claim. So in this case, we learned how to find the expected value. So this is very important because we have the observed, we have the expected that is built with the sample size and the probability of each item. So we perform the chi-square test. And as I said before, these two things are also very important. The observed frequencies must be obtained by using a random sample. Always, always, always random samples are the best unbiased, provide the best unbiased estimators. So, so we are going to use also so we are going to make sure that each of the cells that we are assessing is greater than 5. When they are not greater than 5, we cannot perform this chi-square test. Okay, so be very mindful about that, because one of the cells is less, one of the expected frequencies. If I multiply the sample size times the probability of each one, and then one of them happens to be less than 5, I cannot perform the chi-square goodness of fit test. Okay, so we had an example here that we were doing. So this is my test statistic. I'm gonna subtract the expected from the observed, and I'm gonna square it and then divide it by the expected. So that's how we build this formula. So at the end, the summatory of all these values, so it's gonna give me the chi-square test, the test statistic, and I'm gonna compare it with my critical value, and at some point I'm gonna make a decision. If chi-square is in the rejection region, we reject H naught, otherwise we fail to reject H naught. So that's what we did last class. We built this thing, and then so if you are doing it by hand, so that's what you have to do. So you subtract the expected from the observed, and then square it, and then divide it. So you have to be doing this by hand. I don't think it's fun, and it's more accurate if you do it in Excel. So you can check the results. Many times what happens is when you are typing, you might have typed a number that might not be, so you might make a mistake to get the wrong number. In Excel, for me, it's easier to determine mistakes. And as I said before, this is kind of like the training part, because next time you're going to be using a more sophisticated software. So you are doing the hard work today, but then when you go to the next level, you already know how computers work. So you are going to find this very, very easy to do. So once again, we obtain the chi-square test statistic. We compare it with the critical value. So we reject H naught at the 1% significance. We conclude that the distribution tax methods differs from the previous surveys claim or expected distribution. So so that probably we are rejecting H naught. So so also we saw this part. So this is one particular distribution. So those percentages are giving you a histogram that has a particular distribution. So here we have what is called the rectangular or distribution. So this example, so we are also testing whether or not this bag of candies follows this rectangular distribution. So also called uniform. So if that is the case, so we are going to test whether or not. So we have what in real life we find inside the 500 pieces of candy. So this is what in reality happens. What needs to happen is that we find a 83.3 numbers here. So that means, so each color has to be an average 83.3. Of course, one is going to be 83, and other 84, so on and so forth. So so at the end, we are going to have this, we are expecting this rectangular distribution. We do the test, and we find our chi-square test. We find our critical value based on the alpha and the degrees of freedom. So we realize that we failed to reject the claim, so there is not enough evidence at the 10% level of significance to reject the claim, that the distribution is uniform. So so that is the case. So then we start analyzing our second case. So this case is for independence. So independence is a very important test. You want to know that one variable is not a combination of the other. So we want to know that all these variables are independent. So that the occurrence of one doesn't affect the occurrence of the second. So in this case, what we are going to do is we are going to be using this multinomial experiment, but now we are going to be using contingency tables. So remember, contingency tables are very helpful. So we are going to be what is called stratifying variables. For example, if you are looking at values, let's say cholesterol. So you have cholesterol, and in the general population, you can see that cholesterol is very effective. But then when you stratify by race, ethnicity, or some other age groups, you realize that Lipitor is not, or the cholesterol pill is not, does not have the same effect in everybody. So I want to make sure, before keep, so I want to make sure that these variables are independent. So, so we are going to use the contingency tables. We have rows and columns. So that's what we were doing yesterday. So we have a sample of 2,200 adults. So we have male and females, and we group them as people either eating ice cream with a cup, a cone, a sundae, so forth and so on, right? So we did this part. We also start building the expected frequency. So the expected frequency is going to be found. So the expected frequency is going to be found if I multiply the sum of the row times the sum of the column and then divided by the sample size. So the intersection of these two is going to give me the value of the first cell. In this case, so we are going to have the sum of the rows that multiplies the sum of the column and then is divided by the sample size. So we build this formula and we also say, well, because this number is going to be always the same, I put some dollar signs, and the last one is always going to be the same. So every time I move across, so what is going to change is the value of the column. So I build this formula, I drag this to the left, not to the right. So I'm happy because if I sum all these cells, I get 1,200 males, which is exactly what I have here. So, well, I have here 1,200 males. And if I do the same for women, so I also build the same formula, the sum of the rows times the sum of the columns divided by the sample size. Same thing, these and these are going to be the same. And when I move this cell across, so what is going to be changing is this value. So that's the reason this value remains with no dollar signs. Only dollar signs for the first, dollar sign for the second. So when I drag, so I'm going to see that those are the same. So I made the right computation because at the end I have 1,200 males, 1,000 females, and my sample size is 2,200, right? So I solved this case. So well, not yet, not quite yet, because there are more steps here. So so here we are doing this by hand. So in order to find the first, so we use the intersection. So how many males divided by how many cups. So, and I'm gonna find this number in the expected. So that's what we did here. That's what we did in Excel. So second, so we have number of the total of rows times the total of the column divided by the sample size. So those are the values that I found. So I don't like very much the way these guys present the results because they put all together in in the same table. So of course that can be for convenience, but for me, so we can build two different tables and then have the values more more visual. So in this case, we have the observed, we build the expected, so we have the values for the expected. So the chi-square test is exactly the same as before. I'm gonna have the observed, I'm gonna subtract the expected, I'm gonna square it, divided by the expected, and then do the summatory of all of them. So that sounds like a tongue twister, but so remember here, what I'm gonna do is that this is the observed and this is the expected. So I'm gonna subtract the expected from the observed, I'm gonna square it and divide it by the expected. So I'm gonna do this for every single one. And at the end, I'm gonna add them and I'm gonna find the chi-square. Exactly the same idea. In this case, rather than having two columns, we have two different set of data that we have to compare. So we are gonna find the chi-square. Once again, when I do the, so this is the formula, observed minus expected squared divided by the expected, and that is the summatory of all of them. So we have to make some considerations. Let me keep doing this. So the chi-square independence test used to test the independence of two variables can determine whether the occurrence of one variable affects the probability of occurrence of the other variable. So as I said before, a linear combination of two different variables, let's say A is the double of the first, so probably that is going to be dependent. So every time one changes, the other one will change. So we want to make sure that these cells are completely independent. That so in that case, that this test is gonna make sure that this condition is gonna be met. So for the chi-square independence test to be used, the following must be true. Once again, we need the samples to be random. Randomness, I will not stop saying that, provides unbiased estimations. And then once again, each cell must be greater or equal to 5. So one cell that is less than 5, we cannot use the chi-square independence test, okay? So once again, what we're gonna do here, if these conditions are satisfied, then the sampling distribution for the chi-square independence test is approximated by a chi-square distribution with an R minus 1, C minus 1. So what does that mean? How many rows, how many columns? So we are gonna rows minus 1 times column minus 1. So here, let me go back, we have 1 and 2 columns. Sorry, 1 and 2 rows. So rows is equal to 2 and columns is that, I guess is, we have 1, 2, 3, 4, 5. So we have 5. So my degrees of freedom here, so it's gonna be rows minus 1. So the degrees of freedom. So how we are gonna put this? So the degrees of freedom are equal to the following. I'm gonna say row, sorry, equal row minus 1 times column minus 1, right? So I'm gonna have 4. So I'm gonna row minus 1 is 1, column minus 1 is 4. 4 times 1 is going to be equal to 4. Okay, so that's a very simple math. So my degrees of freedom are going to be given by this condition: row minus 1, column minus 1. So we can have as many columns and as many rows as possible. So when we are computing the chi-square distribution, and this, remember, is for my chi-square critical value. So the critical value is going to be found with the level of significance and the degrees of freedom. And once again, the degrees of freedom in this case is going to be R minus 1 or rows minus 1 times columns minus 1. So where R and C are the number of rows and columns, respectively, of a contingency table. So going to be very simple. We already did the expected. So, so in this formula, O represents the observed and E represents the expected frequencies. Okay. So once again, all these steps we already know. State the hypothesis. We identify the level of significance. We find the degrees of freedom, and then we find the critical value. So remember, we are using the critical value, the Excel formula that we know, so we don't have to do the tables unless you want to do the tables. So once we find the level of significance and the degrees of freedom, we are going to be able to find the rejection region. We calculate the test statistic, we use the data that we have, and then we compare these values. If chi-square falls in the rejection region, we reject H naught, otherwise we fail to reject. And then we have to write this statement. So, so please keep in mind that at some point I am skipping some of these, but if you are answering a question, you have to come up with your statement, whether or not you are failing to reject or rejecting, and what are the consequences of that, okay? So I want you to be aware of that. So in this case, I built a formula here. As you can see, what I did here is basically here. So it's basically here. So I just need to know that my first, should be the rows, and it should be the columns. Should be the columns. So if we have 2 rows and 5 columns, so we should have a 4, right? So this is the formula, and then the critical value we need to, in order to find the critical value, we need to know the chi-square, the alpha value, right? So alpha, we need to know alpha, and let me put the symbol. I'm being very lazy lately. I need to be more organized with this. So we have the alpha. We need to know the alpha for this case, and we find the critical value. Then we have the chi-square test statistic, and then we are going to be able to make the call. Okay. So so let me continue with this. Okay. So once again, this is the critical value. This is going to be my chi-square. At this point, this is the observed data. So very likely I got this in my example. So probably that's what I got in my example. I need to work more. So as I said before, in this case, we find the total of the columns, and then the total of the rows, and then the total, the grand total, okay? So in this case, I just need to confirm in the expected that my values are correct, are matching this. So I build this expected by following the formula, multiplying the sum of the rows times the sum of the columns divided by the sample size. I do this one by one, or as I said, you pay attention and see how you can build your formula. In this case, I know at least 2 of them are going to be fixed. So if I move across, I know that the only thing that is going to change are the values of the column. So that's the value that I left without any dollar sign. So so coming back to my example, so I already have the observed and I already have the expected. So all I have to do is to do this for every single cell. So I'm gonna do the following. So in this case, I am going to say, okay, this is equal, this is the observed minus the expected, then squared, and then divided by the expected, right? So I think that might be, no, it's probably good. So so let me see. Should be there, yeah. So this is B11 is the observed, B17 is the expected, squared then divided by the expected. That's what the formula says. Observed minus expected squared. Okay. So I'm just checking the formula. So I have the first one. So probably if I move, do I have B11, B17? I think I can. Oh. So this is B12, which is B12, B. Okay, that sounds good. So I can just drag this down and it's solved. Okay, so I build the first one. I drag the first formula. This is B11 times B17. The one in the bottom is B12 divided by B18. So it just I just dragged it and I was good. Then I highlighted the two of them, dragged them to the right, and I found the value. So my chi-square, so let's check the value here. Yeah, it's 32,630. So so we are good here. So what we can do here, of course, we have to graph this. So first of all, I need to inspect my case. So in this case, the adult's favorite way to eat ice cream is independent of gender. So the adult's favorite ice cream are dependent on gender. So if we reject age not, well, probably that can be, so the claim is going to be true. So we are claiming that eating ice cream are independent of gender. I was thinking that I don't find any gender related thing, but it seems that there is a gender related explanation for the way of eating ice cream. So probably that might be a vain question, but if you are an ice cream maker, so probably you are going to be interested if you are building an advertisement campaign. So you say, oh, women probably are more likely to eat ice cream, or probably men. I don't know. Gender is important in the consumption of ice cream. So in this case, how do we handle the case? Well, we already have, so let me erase these things. So what we have here is, let me go back. I think it will be better here. So in this case, the level of significance I didn't put is 1%. So I'm gonna do this at the 1% level of significance. So I already have my rows and columns and the degrees of freedom. So my level of significance is gonna be 1%. So I am going to map this, build the graph. So in this case, so what we need to do is to make sure that the results are there, and Excel is very smart and gives me the result, but I need to know if I am making the proper call, right? So I'm gonna This is my chi-square distribution. Remember, the chi-square distribution is skewed. So we have, this is my chi-square critical value. So my critical value is here, the chi-square critical is going to be equal to 13.277. So it's not that unusual. We are using in the previous and this one, the 1%, and the critical value happens to be the same. So, so there is no surprise here. So we have a chi-square test that basically is somewhere in here. The chi-square that we found is going to be 32.6. But I cannot write anything else here, I guess. Um, 32.6, right? So we have so we are rejecting H naught. So and we write so our chi-square statistic, as we mentioned here, is 32. My critical value is 13. So that number falls inside of the rejection region. So I reject H naught. So so I reject H naught. So there is enough evidence at the 1% level of significance to conclude that adults' favorite way to eat ice cream and gender are dependent. So as I said before, you might be producing ice cream, you might be the owner of a supermarket, you see those results, you say, okay, so I know what kind of things people like. So, so these tests are always, they always have very specific applications. So, so we are going to be applying this a lot. So I think I don't want to keep you guys way too long. I think that's all the work that we can do for the semester. Um, so if you have any question, please let me know. If you don't have any question, I will conclude the semester. So once again, I want to thank you, many of the, almost, well, not almost, all the students. I know that, and I have emphasized this way too many times,